After all the preparations, we are now ready to parallelize the fast Fourier transform. And to parallelize, we need to choose a distribution of the data. And the data in this case is a vector, because it's the vector that we're going to change from the input vector to the output vector. You may recognize in the picture two different distributions. On the top, the block distribution, and on the bottom, the cyclic distribution. We assume here that the number of processors, which is 4, is a power of 2. We also assume, like in the FFT, that n, the vector size, the vector length, is a power of 2. And in the picture, we denote the butterflies by little arcs. For example, on the top, you see for k equals 2, the butterflies combine neighboring components of the vector. For k equals 4, the components that are combined in a butterfly are at distance 2. And in general, for stage k, the distance is k divided by 2. Now what you see on top is that if we use a block distribution, then the small butterflies, so at distance 1, 2, up to actually n over p, they are local. The elements that are being combined reside on the same processor. And that's useful because then we do not have to communicate to perform the butterfly operation. On the other hand, when k becomes large, the block distribution doesn't work anymore, because then we combine components that reside on different processors. But then the cyclic distribution comes to our rescue, because there you see that if we have k equals 2p, then the elements to be combined are at distance p. And this, in the cyclic distribution, is exactly the same processor. So there we see that, for example, that the black processor has the elements 0, 4, 8, etc. So combining 0 and 4 is a local operation. So the cyclic distribution works for 2p and also for 4p up to n. Here we see this in terms of matrices. If we take n equals 8 and we have 2 processors, then in stage k equals 2, we multiply the vector x by I4 times B2. And B2 is actually a matrix with 1, 1, 1, minus 1, 2 by 2 matrix. And you see 4 copies of this on the main diagonal. Now the blocks that contain the butterfly blocks, they are 0, 1, 2, 3, and they are on processor 0. And the other ones are on processor 1, so they are local. So that's why it works. On the other hand, if we perform the last butterfly stage, then we have 1 copy of B8, and here you recognize the identity matrix on the left upper corner, also on the lower corner, and the omega matrix on the right, and also minus omega. And there you see that the distance of the elements to be combined is exactly 4. So there, for example, x0 and x4 are being combined on processor 0, and this is a local operation. So the cyclic distribution works here. Now a question to you. How would you organize the parallel algorithm to perform the unordered FFT, that is the butterfly part of the FFT, without a bit reversal? So from right to left, first you do a number of copies of B2, then of B4, and you end with Bn. How would you do that? Well, you may have thought about this, The logical thing to do would be to start with the block distribution, then at some point move to the cyclic distribution and finish in the cyclic distribution. When should you move? You may have some freedom, but when the block distribution runs out of steam, that would be a good moment. So for k less than n divided by p, you use the block distribution, and then you move over. So will this always work? This will work if the block distribution reaches k equals p, because then the cyclic distribution can take over and continue from 2p onwards, 2p, 4p, etc. Each time it doubles. And that means that we need to have that p is less than or equal to n over p, because we run out of steam after n over p. And this means that we have the condition that p should be less than square root n, which in practice usually will be the case. For example, if p equals 1020, if p equals 32, then or less, then you can do the n equals 1024. So usually you have much larger problem sizes than you have numbers of processors. Now, if p happens to be larger than square root n, you first of all should ask yourself, do I really want to solve this small problem with that many processors? But if you really want to, there is a way of doing that, because then you need more distributions, something in between the block and the cyclic distribution. And that would work. In the book, this is discussed, but here we'll leave it for simplicity. And then we actually do have already a parallel algorithm, because we had a sequential algorithm, which you will recognize the inner loop is almost the same. But here we run the algorithm only for our own data as determined by the block distribution. So this is an algorithm for processor S. And you will see the S in the second loop for R equals S times B, that it really depends on S. It depends on which processor I am. So what do I show here? Superstep 0 of the algorithm is all the computations in the block distribution. And at the bottom you see superstep 1, where we move from the block to the cyclic distribution. This is a communication superstep. So, and the next slide will show you the finishing of the algorithm. Now the start, superstep 0, it runs for k up to n divided by p, like we just saw, because then we can use the block distribution. Now we define B, which is the number of butterfly blocks per processor. Remember, a butterfly is a matrix in stage k. It's a k by k matrix. And we have n over k copies of this. Now if we have p processors, every processor has to perform n divided by kp butterfly matrices. And so that number is B. And then we just distribute it by the block distribution. And that means that we have R, which is the number of the butterfly block, and that's divided by the block distribution. So if I'm processor S, I have all the butterfly blocks numbered from S times B up to S plus 1 times B minus 1. And for that butterfly block, we just perform the computations, the sequential computations, as we have seen before. So I won't go into the details. Then after the redistribution to the cyclic distribution, we perform more butterflies up to k equals n. So that's what the while loop tells you. And we perform n over k butterflies. And in this case, every processor does part of a butterfly. It doesn't do a complete butterfly. It does the part that belongs to its own cyclic distribution, its own data. So we compute the local part of the rth butterfly, and that's why you see that in the for loop you start with S. That's in the cyclic distribution. You run over indices j equals s, s plus p, s plus 2p, etc. And that explains this for loop. And then inside the for loop you recognize again what we have to do. And the nice thing is these are local operations. There's no communication happening here. That's the whole algorithm. The whole algorithm, not exactly. There's one part that we didn't talk about. That is the bit reversal. So the bit reversal occurs in the sequential algorithm, but also in the parallel algorithm. And the example that I show here is for 8 processors, and n is 256. And we'll just take a component xj, so I write the j, which is 46. In binary, it is written as 00101 110. And the little subscript 2 means this is a binary number. And what you want to do is you want to move this xj to a position which is the bit reverse. So we want to move it to position 116, which in binary is 0111 0100, which is the reverse of the j that we had previously. Now, the interesting thing is that we can do this in a nice way if we start in the cyclic distribution and end in the block distribution. And it's nice ending in the block distribution because then the following butterflies have the right distribution. So we want to start in the cyclic and then end in the block distribution. And how do we do such how do we perform this bit reversal? Now let's have a closer look at the bits. We have 8 bits because n equals 2 to the power 8. And we can group them. In the cyclic distribution, for example, in this case we have 8 processors, we take the number modulo 8 to determine which processor owns that element. So that's the last 3 bits. That's taking modulo 8. So the last 3 bits are 110, and that means that processor 6 owns this element. And it has a local index, which is the 00101. Now, if we bit reverse, one way of doing this is we bit reverse the local ones, swap the bits from the processor part and the local index part, and then we bit reverse this, and we get the final result. So swapping the local indices doesn't need any communication. So that's from the top to the part below that. We just do a local bit reversal. And we're still in the cyclic distribution. But swapping the 2 parts, basically nothing happens. Because we say we start in the cyclic distribution, we don't do anything, but then we decree that what we have is a block distribution, where in the block distribution it's the top part, the leftmost part, that determines the processor. That's a property of the block distribution. You divide by n over p, meaning that the topmost, the most significant bits, they determine which block. This is not exactly yet the block distribution, because we want the block distribution to be in a bit reverse of the processor number, and that's the last step. We move 110 into 011, and that's the block distribution. So if we want to carry this parallel bit reversal, if we want to carry this out, what do? we start with a local bit reversal, and then at the end we swap the data between the processor S and its bit reversed processor. And then we don't change anything of the indices. And that gives the desired output, and that's the start for the butterflies. Okay, and now we do something that a lot of customers like when they go to the supermarket. You want to buy two, but pay only for one. We can do two permutations, one after the other, at the price of one, because we just compute what the overall permutation is, the product of those two, and that's what we carry out. So that would be our aim. We do a redistribution within the butterflies going from block to cyclic. And we do, within the bit reversal, we also perform a permutation. We swap the data between the processor and its partner. Now, all the processors at the start, they perform the same operations. They have their data, a number of butterfly blocks, and for every butterfly block, they perform the butterfly operation. So I'll scratch your back if you scratch mine. The processor that has the data in the block reverse distribution just performs all the butterflies that its partner has to do, and the partner does the same for this processor. And only then this bit reversal swap, the swap between pairs of processors, happens, and it's combined with the move to the cyclic distribution. And that way we have less communication, we save a superstep, and we have a parallel fast Fourier transform which includes the bit reversal, but still has only one communication superstep. So what is the total cost? We have 3 supersteps, so the synchronization time of this algorithm is 3 times L. And actually only one of those supersteps is a communication superstep. That's the bare minimum. The communication time, well, every processor has n over p values, and they're complex values. So it's each with a real and an imaginary part. So we have 2n over p local data, and in the worst case, everything moves out, and something comes instead of that, moves in. So that means that we have an h relation with h equals 2n divided by p, and the cost will be 2n divided by p times g, the communication cost per data word. The computation time is very simple. We don't really need to count. We have the sequential time, 5n log n. We have perfect balance in the algorithm. All processors do the same, exactly the same number of flops. That's because we have these assumptions about powers of 2. And so the total time is 5n log n divided by p. We also don't have any extra operations like redundant operations. So that's a good result. So to summarize, you've seen here an algorithm where we use different distributions in different parts of the algorithm. By postponing some communication, we could actually combine it with another communication and reduce the amount of communication. So as a result, we have an FFT algorithm that starts in the cyclic distribution. At some point, it moves to a cyclic distribution. So it starts and ends in a cyclic distribution. And that's very useful. The input is in the same format as the output. You can chain the fast Fourier transform to perform more after each other, or perform an inverse transform if you want. That's all very easy that way. Now the total BSP cost of the algorithm is 5n log n divided by p, plus 2n divided by p times g, plus 3l. A final question to you. We didn't formulate the algorithm yet for the redistribution from block to cyclic. Can you do that? As a notation, we use for the bit reverse processor of processor PS, my partner, we use the notation P of row S, and row has a subscript P saying it's the bit reverse where we have a maximum number of P.